Okay, in this video, we're going to explore the idea of electric field strength. Electric field is a really abstract idea. This is an invention of Michael Faraday, who was trying to this is the thing about Faraday. He was a very physical person. He really thought mechanically about how the universe worked. And so he really was trying to understand, how can you have two charged objects and they can exert a force on each other, and yet they don't even need to touch each other. They can be at a distance away. That's referred to as a force at a distance. Gravity works like that. Electric field works like that. Magnetism works like that. Somehow objects are able to exert a force on each other even though they don't come in contact with each other. And that was really hard for Michael Faraday to understand. So what he imagined was that there must be this thing that surrounds all charged objects. And he referred to that as the electric field. Okay, now that's a very abstract thing. It's certainly very hard to visualize, although we'll look at some different ways that you could visualize it in the next video. But ultimately, the idea of the electric field is a good idea. Basically what Faraday was saying is that the objects don't interact with each other. It's their electric fields that interact with each other. And because those fields stretch out across space, they can feel the electric field of other charged particles that are reasonably nearby. And as a result of that, there'll be a force that will act on them. That's how the force is transmitted from one charged object to another charged object. Now, the electric field itself is kind of hard to visualize. It's a little abstract, but the electric field strength, that's much, much more concrete. It's not as abstract. There's a process in which we can measure how strong is the electric field, and we really just need to give it a definition. So this definition that we're about to look at for electric field strength, this is just made up. Okay, it's not something that just exists in the universe. It's just we need to have a way to imagine, if this electric field is real, if it really is there, then how can we know how strong it is? Like, we have to have some system or some mechanism for knowing how strong the electric field is surrounding an object. And so the way that we define the electric field strength is we imagine how much force would act per unit charge, and per unit charge just simply means per coulomb. So force, which will be in newtons, divided by, per means divide by, the number of coulombs. Let me give you a similar analogy. So if you imagine, let's say you were making a drink and you're using some kind of powdered or flavored powder. So you put a little bit of the powder in, you'll see that it starts to turn color and it has the color of that powder, but it's pretty light. And then you put in more, and then you put in more and more, and it's starting to get darker and darker. You see more and more of the color of this powder that you're putting in the liquid. Okay, well, how would we measure the strength of that? That strength would be referred to as concentration. Concentration is very similar to electric field strength. It's how much of this thing there is in a given space. And so what we would do with the Kool-Aid in the drink is that we would measure how much Kool-Aid per liter that I put in, and that would tell you how concentrated that particular drink was. So the bigger that number per liter, the stronger the concentration of the Kool-Aid. And in a similar way, the electric field strength uses the same thing, except instead of per liter of something, we do it per unit charge or per coulomb of charge. So that is to say that if I had 1 coulomb of charge and I had an electric field strength of 5 newtons per coulomb, that means that my 1 coulomb charge would feel a force of 5 newtons. It's pretty straightforward. It is the force that acts on a charge, and then it includes that it must be acting on a small positive test charge. Now, the first portion of it is the math, so it's going to be F divided by Q. And let's think about the units of this thing. Now, in some cases, we have properties that get special names for their units, like the Newton, for example, is a derived unit. But in this case, we don't give a special name for the units for these. They're just referred to as newtons, because that's the unit for force, divided by the units for charge, which is coulombs. It doesn't get a special name. It's just newtons per coulomb. You would say it exactly like that. But the issue of it being on a small positive test charge is the idea that it's small is because all charged objects produce their own electric field. And since we're trying to test out some other electric field, we don't want the object that we're bringing in to distort the field too much. Let me give you an analogy to that. Let's say, for example, you wanted to measure the gravitational field strength of our moon. You want to know how strong is gravity on the moon, the gravitational field strength, right? It's a similar kind of property, except involving the masses of objects. Well, you would want to bring a small object to test it out, because if, let's say, for example, you brought the Earth and you put the Earth on the moon, well, the Earth has its own very strong gravitational field. So you wouldn't really be measuring the moon's gravitational field. You'd be measuring some combination of the Earth and the moon's gravitational field. So similarly, when we're trying to figure out what's the strength of an electric field, we don't want to bring in a large charge, because a large charge is going to produce its own electric field, and it's going to dramatically distort. And you'll see that when we look at the video on field lines. It's going to really distort the field around this charged object, and that's what we're trying to avoid. So we want the charge to be very small. Now, the issue of it being positive, that is just simply by convention. Basically, Ben Franklin sort of based everything on the positives. You know, it's different with mass, because when you talk about gravity, there's only one kind of mass. Like, that's essentially it, the gravitational mass. But in this case, there are two types of charges that react in exactly opposite ways to each other, both positive and negative. And so there had to be an arbitrary choice. Which are we going to base this on, the positives or the negatives? Ben Franklin chose to base everything that he did on the positives, and everyone else just kind of followed along in his convention. Now, today, if we were to do it, I think almost anybody would say, well, we should base it on the negatives, because the negatives are the ones that really do all of the moving. The positives do very little moving. They just sort of vibrate in place, but they don't really go anywhere. So today, we probably wouldn't say it was based on the positives, but this is the convention that we use throughout all of science, and so we're going to continue to use that as we go forward. We're always thinking about what would happen to a positive charge at that point. That is going to be the direction of the electric field, and we'll look at that more when we look at the electric field lines. So let's take a look at a few quick examples. Let's say that, for example, you have a small test charge, so a 2 microcoulomb charge, or 2 times 10 to the minus 6 coulombs. You placed it in an electric field, and you found that it experienced a force of 34.5 newtons to the west when it was placed in our room. So what we want to know is, well, what's the electric field strength as a result of that that test charge? We're going to put this test charge in room 346. We're going to measure the force on it. Here it is. And then we're going to use those two to calculate the electric field strength. So in this case, Q is equal to positive 2.0 times 10 to the minus 6. Don't write the microcoulomb when you make your list. You should always just translate it into the numbers that you need to use when you actually make the calculation. We don't plug microcoulombs into the calculation. We plug in regular coulombs. The other thing that we were given, though, is the force. That was 34.5 newtons. And what we're looking for is the electric field. So in this case, there's no algebra to do. We're just going to plug the numbers in. That's 34.5 divided by 2.0 times 10 to the minus 6. One thing I want to point out is that I did not plug the negatives, the positive sign, I should say, in here for the charge, because again, we never plug in the positive or negative for the charge into any of the equations in which we're trying to mathematically model what's going on. We just put the number in, and anything involving the direction of the force or electric field or whatever it is that we're looking at, we will get that from just thinking it out. We'll just reason out based on what happened in the situation or what the charges that were present, what is the direction of this electric field or this electric force. But we're never going to plug in the sign of that charge. So let me turn on the calculator and let's clear this. So we have 34.5. Sorry, let me move this up a little bit so you can see a little more clearly. And now we need to divide it by this number in scientific notation. So that's going to be divided by 2.0 second function EE. And now it wants to know the exponent. That's a negative 6. And that says 1.725 times 10 to the 7th. So cutting that down to the correct number of sig figs, that would be 1.7 times 10 to the 7th newtons per coulomb. The electric field strength. That's a huge number. That's a huge number. Electric fields are typically, the kind of electric fields that you're going to experience are going to be fairly large. The old style of TVs produced an electric field that was at least about 100,000 newtons per coulomb. So this is a pretty strong electric field, but it's not crazy strong. It might seem like that's a huge number, and it is a big number. But compared to other electric fields that you might experience in your daily life, that's not that huge of an electric field. To put it in perspective, the electric field inside of the atom is literally millions of times stronger than the electric field that we're looking at right here. So while this is a relatively big number, that's like pretty average, I would say, as far as the strength of an electric field. Let's take a look at one more example, and I particularly want to look at this example because this is a way that we're going to use this equation quite frequently. So in this case, we have a negative 4.3 microcoulomb charge is being placed in an electric field where we know the strength. So I'm going to give you the strength is 9.16 newtons per coulomb to the north. We want to calculate the electric force acting on the charge. So in this case, we were again given Q, That's negative 4.3 times 10 to the minus 6. And then this time we were given E. So the electric field is 9.16 newtons per coulomb. And what we're being asked for is the force. This equation is essentially the same thing as the equation for weight, right? Because weight is essentially the gravitational force. So you have this equation that says that the force of gravity, or W, is equal to m times g, right? M being the thing that causes the gravitational field, and g being a way of measuring the gravitational field strength. And we multiply those two things together, we get the force that acts on that mass in a gravitational field. Here's the exact same thing. Look, this is the equation. E is equal to F over Q. So if we wanted to solve this for F, all we would need to do is multiply both sides by Q. And we would end up with this equation. Q times E, right? Now you don't need to write this, but this is just exactly the same as W is equal to mg. Here's gravitational force. Gravitational force is the mass, which is what feels the gravitational field, and then multiplied by g, which is a way of measuring the gravitational field strength. Here we have the same equation. The force, I wouldn't call it the weight, it's certainly not the weight of the object, but it's the force that is caused because charged objects can experience a force from electric fields. So when I place this in an electric field, I will get a force on it. The W equals mg equation is the same version of the equation for gravity that the F equals QE equation is in this world. So this is a really important version of this equation because given an electric field and knowing what the charge on something is, I can tell you what the force is going to be experiencing, that charge will experience. And as a result of that, then we can work out things like, for example, what will be the acceleration of this object? How fast will this object be moving after a certain distance or after a certain period of time? So this equation is really important, just a variation of the E equals F over Q equation, but very, very useful equation. So in this case, F is equal to Q, which is 4.3 times 10 to the minus 6. Again, I don't plug in the positive or negative sign. And then multiplied by 9.16. So let me bring out my calculator. So in this case, we have 4.3 second function EE to the minus 6 times 9.16 equals, and that says 3.93. So in this case, the force is going to be 3.9 times 10 to the minus 5th newtons. Pretty small force, but realize this is a small object. I mean, the objects that we're charging up are tiny little pith balls or pieces of tape or something like that. So these are very small objects. So even though the force is not very large, that's a very significant force acting on these objects, whether it's a pith ball or a piece of tape or whatever the small object that has become charged. Now, this is the definition of electric field strength. These are two useful ways that you may use the equation, but let's take a look at an alternate way that you might use this equation for electric field. The idea behind this is that I don't know where the electric field is coming from, so my only thing that I can do is to take a test charge, put it in the electric field, and then measure the force. Maybe there's a force acting on it in this direction. And then based on that force, I can kind of work out, okay, well, this is about how strong that electric field is by looking at the ratio of the amount of force that was exerted on this charge that I placed in the electric field. Let's take a look at what happens if you do know where the electric field is coming from. Let's say that you do know where the charge is that's causing the electric field. Well, that is not the same charge that is in that equation. So let's take a look at the way that equation worked again. Essentially, you have E is equal to F over Q. But remember, all charged objects create an electric field. So the reason why there's a force between these two is because there must be some other second charged object. There must be two charged objects. So in this case, what we're going to do is we're going to make a substitution. Okay, so here's the force, right? And here's the force, right? This is the same force we're talking about. Okay, this is not some magic force that just appears out of nothing. If there's an electric field, it is because there is some other charged object nearby. The only reason electric fields exist is because of charged objects. So in this case, we're going to substitute the formula for the force between two charged objects, which must exist if there's an electric field being experienced by a small test charge, then there must be a second charge that is creating that electric field. So when we make that substitution, we end up with KQQ over R squared. That's the F part. Now divided by Q. So these two guys are going to cancel out. I'm going to end up with KQ over R squared. Okay, so this gives us an alternate equation, and one of the things really important to understand about this equation is that this is not the same Q as in the other equation. This is the test charge, and this is the source of the electric field. This is the one that is causing electric field. And this equation is much better than this one, because in this equation, the only way you can get the electric field is you have to go and test out and just keep constantly recalculating over and over and over again after you remeasure the new force that's exerted on your small test charge. This one's much better because now I can tell you the electric field anywhere, and I don't need to test out anything. You just tell me how much charge is causing the electric field, and you tell me how far away do you want to know the electric field strength, and I'll just plug it into this equation and calculate it. I don't need to keep retesting over and over and over again to know the field strength in different places. So ultimately now we have two equations for electric field strength. One of them is F divided by Q, and the other one is KQ over R squared. I'm going to put a box around these. These are our two equations. You'll see them on all the tests and quizzes or in the data booklet or in the equation sheet. But I do want to make one quick comment on that. This Q is a test charge. But that Q is the source of the electric field. Okay, so they are not the same Q. One of the Q, they're both the Q's from the F equals KQ over R squared, but one of them is the test charge, that's this guy down here, and the other one is the charge that created the electric field. So let's take a look at how you would put this into practice. We'll do a really simple example problem. So let's say, for example, that we have a electric field strength. We want to calculate the electric field strength 15 centimeters away, or 0.15 meters away, from a 12.8 microcoulomb electric charge. Okay, so in this one, again, we were given R is 0.15 meters. I don't want to put in the centimeter number because the K now, I'm going to plug this number into an equation that has K, and K is not in centimeters, K is in meters. So very important to always use the distances in meters. And then the Q is equal to positive 12.8 times 10 to the minus 6 coulombs. And then what we're looking for is E. Okay, so still have a charge, but not the same charge that I had in the previous equation. So this is KQ over, R squared. Let's plug in all the numbers. K is 9.0 times 10 to the 9th. The Q is the 12.8 times 10 to the minus 6. And then the R is 0.15, and then don't forget that you need to square this. This is a really common mistake, is that people write the equation perfectly correct. They write the number incorrectly, but then they don't write the squared here, and then they don't calculate it that way either. They don't calculate the answer using the squared on the bottom. So we'll clear the calculator. This is 9 second function EE to the 9 times 12.8 second function EE to the minus 6 equals, divided by 0.15 squared equals, and that gives us an answer of an electric field of 5.1 times 10, and this is to the positive 6 newtons per coulomb. So a pretty decent field, 5 million newtons per coulomb electric field strength. So fairly high electric field strength. You know, one of the things that you may be asked to do with this equation, though, is just like we did in the previous example, I might give you the electric field and ask you, well, then what's the charge that produces this electric field at this given distance? You have three variables, essentially, E, Q, and R. So two of those would have to be given to you, and the third one you'd be solving for. And of course, K is a constant that's always going to be given to you on the equation sheet or in the data booklet or on the top of the assessment itself. So this is the way that we calculate electric field strength in terms of its intensity. And now you just need to practice some of these on your own, and I'm sure you'll master it very quickly.